for this chapter is still easy, I think. So only five sections in this chapter: the current and current density, resistance, resistivity, Ohm's law, power, semiconductor, superconductor. Most of the topics should be covered in circuit analysis, I think, and except this one and this two, but this two is not really important for this course because you have not much calculation about this stuff. Although I may show you some beautiful poster about the semiconductor, which I have shown to the high school student in Macau in July, and which is about some semiconductor physics. So first of all, the electric current. Any isolating conducting loop, regardless of the whether it has excess charge, it is all at the same potential. So actually, so for this loop, there are no current, no electric field, no at all. So they are at the same potential, and this is very great because it is very easy. But the physician or the scientists are very naughty, so they want to make things not so easy. So they try to put a battery there. As you know, you can have many kinds of battery, so it has a potential difference between the positive side and the negative side. So there are voltage difference at this point and this point. So the electric field act inside the material make up the loop and exerting the force of the on internal charges cause them to move and thus establish a current. So as long as there are voltage difference between these 2 points, then the electron or whatever will for metal for conductor, usually the free electron will move, but actually it is in the opposite direction with the current, because when the physician invent the current, they don't know there are electrons in the world yet. So they usually assume there are some positive charge moving around this loop. But actually, you can you should be able to understand it should be some electron going this way, counterclockwise. So there are some current, but the current direction and the moving direction of the electron are in the opposite. And actually, we define the current is something like dq over dt, the derivative of the charge with respect to the time. And so it is simple. So it means that when the charge are moving at a unit time, then it is the current. So this formula is simple to understand. And for this one, a conductor with a current I0 on this path, splitting at the junction into 2 branches, like this way and this way. So it will satisfy I0 equals I1 plus I2, which means the total current flowing through a node will equals to the total current flowing out of the node, which is known as the Kirchhoff's current law, KCL. It is not the KCL in chemistry class, not the potassium chloride. It is Kirchhoff's current law, KCL. And I suppose all of you, at least for all the ECE students, should have learned the KCL and also the KVL in circuit analysis. And you use it throughout the whole semester. And of course, the Kirchhoff current law is KVL should be referred to Kirchhoff voltage law, which is a little bit different, but I think it is quite simple to understand. So now we need to define the current density. For this definition, it is a little bit weird because usually when we define something, for example, in this case, it's current density, the J, usually we will define it as J equals something, but actually we cannot do this for the current density. The definition for current density is something like the J is inside the integral here, and I is equal to this surface integral. It is something like the electric flux when you learn in the chapter of Gauss law, when at that time here is E, the electric field dot dA equals the total flux. And if it is a closed surface, it is a net flux, something like that. But here, current density is of course a vector, and the current will be the integral of the current density. And actually, for a wire, you define a cross section. You define the taking over any surface cutting across a conductor. So suppose there's a wire or a pipe, something like that, you define a cross section and then you integrate the current density over the surface, and then you will get the current. Although in certain cases you just forget all the field, you only know of I, V, something like that, which is the long circuit parameters. And in this case, J is something similar to E, which is also a vector. So when you calculate this integral, it is similar to calculating the electric flux. So when the same direction as the velocity moving charge, if they are positive charges, the opposite direction if the moving charge are negative. So also in this case, you need to define the area. What is the direction of the vector? Maybe, for example, so for this one, if we define A is here for the this is cross section, so it looks just a line. So so actually, when you have the J will be something like this, then actually you have the area vector, something like dA, pointing to the right side. So you will have the positive current. If you define in the other way, then the current will be negative. So you need to care about the definition of the direction of the area vector. And here you can see that for this cross section, this is broader, and for this part, this is narrower. So you feel that the current here will be faster. You can imagine this is a river and water flows through it. Some of you may be the civil engineering student, so you may have learned the fluid dynamic and the Bernoulli's law, but for easy student, I don't think you learned the Bernoulli's law throughout your bachelor study. But yeah, they are a little bit similar in this case. So for this page, we try to see the current density in a microscopic view, we try to zoom in the wire, and then we can see the electron. We can see the electron. And actually, conducting electrons are actually moving to the right, but the conventional current I is said to move to the left, as I mentioned in some pages before. So here we assume the current is going from right to left. And in this case, VD is also from right to left. We assume here is a positive charge moving from the right to left. And actually, we have electric field. This the right side is higher, and the left side is weaker. So that suppose it is a strong E on the right side and a weak E on the left side. So for positive charge here, then it will be moved from right to left, pushing by this E field. And actually, the current density is also from right to left. So here we calculate the total amount of charge, which is something like this is the charge of a particle. Maybe it's just a proton, or although if you learn chemistry, you know proton shouldn't be moved, but here we just would assume this is E, but actually E should be moving from left to right instead of right to left. But actually, you need to consider it's an electron, because if you imagine it is a proton moving from right to left, then the mass are totally different. Then the physics might not be correct. So here you can assume it is an electron here, and then this is the volume. This is the volume. A is the cross-section area. L is the length of this part, and also N is the electron density in a unit volume. And suppose the time an electron move from here to here, from A to B, is supposed to be T, which is L over VD. Simple math. The distance divided by the velocity or the speed. So current is I equals Q over T. Just now it's dQ dt, but we assume Q is constant. The rate of change of charge is constant, so it's just Q over T. So we substitute this one here and also this one into here. So we have this one over this one, and L can be cancelled. So it is something like this. And J equals to I over A. J equals to I over A. Because when we assume J is uniform, so I will be equals to JA. So J is equals to I over A. And so we just divide A on both sides. So J is NE times VD. And we can write it as a vector form because J is a vector, VD is also a vector. J, yeah. J should have the same direction of I, although I is not a vector, but we will have some direction for the I. Assume No. I think you have the idea. I has the direction, but it's not a vector. But I should have the same direction as J. For here, we assume all the stuff are positive charge particle. But actually, in your mind, it should be a moving electron. DA 是 yeah, because you have J dot DA. So if J has the same direction of with DA, then this one is positive, and this is also positive. I equals something like this. But it's just minor, so you need to make sure the positive negative is correct. It should be. I suppose this is the most complicated part of physics, rather than the math. You need to make positive or negative correct is difficult, in my opinion. So we get this equation, which is very important, but I don't know why. So actually, so we have this equation, J equals NE times VD. The product NE has the SI unit Coulomb per cubic meter, meter to the third power. Is the carrier charge density. So let's have some simple calculation. So for this one, the current density. The current density in a cylindrical wire of radius r equals 2 millimeter is uniform across the cross-section of a wire, and J is uniform, which is equal to 2 times 10 to 5 ampere per meter square. What is the current through the outer portion of the wire between the radial distance r divided by 2 and r? So it asks you the current at this part. So it is simple. So maybe we write A prime should be pi r squared minus pi r over 2 squared. So simple, the large circle minus the smaller circle, then it will be the area of the ring, right? So we substitute all the number. This is 2 times 10 to minus 3 square minus 3 square, something like this. 勇者。So, so this is 9.42 mu m squared. Then I will be JA prime, which is 2 times 10 to 5 times 9.42 mu, which is 1.9A. So this is a student example. It's uniform current density. So for this one, it is a normal difficulty. So J is not uniform in this case. J is A R squared. And A is 3 times 10 to 11. A over meter to the fourth. And actually, it asks you the current through the. Now, what is the. Yeah, it still asks you what is the current flow through the same outer portion of the wire. So from R over 2 to R. So in this case, we need to do the integration J dot dA. So J is parallel to dA, so we can just simply write J dA. And we substitute J is AR squared. And dA is equal to R dr d theta in a polar coordinate. You can imagine like this. So for polar coordinate, this is dA. This part is dA. This part is dA. And this is the R. And this is d theta. This is d theta. Okay? So when we need to calculate the area of this part, and also this part is dr, which is so from the original point to this part is r, and the small incremental length is dr, and actually no. This angle is d theta, and this is the small incremental angle d theta. So when we need to calculate this one, and suppose dr and d theta is sufficiently small, we can consider this is a rectangle. Although it is not really a rectangle, but it is small enough, we can approximate it to be a rectangle. And so the height is of course dr, right? The height is dr. And this one, I suppose you learned in high school, for a sector, this one should be equal to r d theta. The radius of the sector and times the angle and it will become this length. So this is r d theta. This is r d theta. R d theta. So actually, dA is r d theta. And for a complete circle, it will be something like r dr d theta. For dr, we are integrating from r over 2, from r over 2 to r. And for the theta is this angle. So it will be from 0 to 2 pi for the whole circle. So dr should be integrated from r over 2 to r. d theta should be integrated from 0 to 2 pi. And actually, most of the parameters are independent. So with something like this, then it will be A, and this is 1/4 r to the 4th, so it will be r to the 4th minus half of r to the 4th. Yeah, this is the integration for the first part, and the second part will be 2 pi, because you integrate 1 d theta, so 1 times 2 pi minus 0. So actually, 2 pi is this part, this integral is this part. And you substitute a equals to 3 times 10 to 11, and r equals to 2 millimeter. 2 millimeter. I do not write it out. And the answer is 7.1a. 7.1a. Any questions? 上一页。好了吗？ Any questions?
每次都定 dA 的方向跟电脑方向相同的话，那为什么还要编程呢？那不就直接用后面那个就可以了吗？
其实是可以的，但是这些就是最简单的 case 啊，所以你不知道哪一天你画不出来的话，你就 sometimes you cannot draw it explicitly, then you need to rely on the math rather than a graph. Then you need to determine positive or negative by the math itself. Any questions? So for this one, what is the drift speed of the conduction electron in a copper wire with radius r when it is uniform current I equals 17 mA? Assume that copper atom contribute 1 conduction electron to the current, and that current density is uniform across the wire cross section. Of course, we need to use n equals Vd in this example. first we need to calculate is this one, this one, this one. So let me explain this first. So we really want to calculate the atom per unit volume, which is what we need for this equation. We need the n, so we calculate it first. But how do we calculate it? So we can know that we have Na, which is the Avogadro number, which you should have learned it in chemistry, 6.02 times 10 to 23. Molecule or whatever per mole. So this is Na, which is atoms per mole, and then you also need these two numbers from appendix F. So the first one is the mole per unit mass, which is referred to the copper. The density of copper is 8.96 gram per centimeter cube. And mass per unit volume is the molar mass of copper, which is 63.54 gram per mole. So suppose you get all these three numbers, then you can plug it in this equation. So it is so this is 6.02 times 10 to 23, and times 1 over 63.54 times 8.96 times 10 to 30. So it will become 8.49 times 10 to 28 meter to -3 power. So it means in 1 meter cube there are 8.49 times 10 to 28 electrons in this volume. So we can calculate Vd to be equals to J over Ne. So this one is due to, this is Cm cube. Cm cube is 1/10 of a meter. So this is cube, so you need to multiply 10 to 3 so that it is gram per meters cube. And then we can substitute J equals I over A. So it will become NE A. Then we plug in 17 times 10 to -3 over 8.49 times 10 to 28 times 1.6 times 10 to -19 times pi. A is pi r squared. So it will be what is the r? R is this one. 900 mu square. I don't have enough space. So finally, we get the answer is 4.9 times 10 to minus 7 meter per second. So it is very, very slow, which means the electron is actually moving with this speed when the copper has a current like 17 MVA. So the electron is slower than a snail. But actually, this is a practical case. Maybe you confuse how come the electron is moving that slow. Actually, for example, suppose we need to switch on the light. For this classroom, the light is very slow because there are some control circuit, something like that. But actually, for example, if you are at home and then we want to switch on the light, actually this is something like the simultaneously when you switch on it, and then you can see the light almost immediately. Actually, the electron doesn't really need to go from one point to the other. Actually, it tries to move, and then the electron before it also move, and then to form the whole loop. So it doesn't mean the electron really need to move from the positive to the negative. So for this part, it is about the resistance and resistivity. So if we apply same potential difference between the end of geometric similar rod of copper and of glass, very different current results. The characteristic of conductor that enter here is the electric resistance. The resistance R of a conductor is defined as R equals VI, which is what you have learned in circuit analysis, the Ohm's law, V equals IR. Actually, the resistance is not only related to the material itself, but also the geometry of the element. And actually, this is very simple. The resistance equals to the voltage, the voltage or the potential difference across this conductor, and I is the current through the conductor. So they are proportional. If I increase, we should increase at the same ratio. So for this one, we also define the resistivity. So the difference between resistance and resistivity is that the resistance is not only related to the material itself, but also the geometry. However, the resistivity only relates to the material itself. It don't care about the geometry of the conductor or the device. So in this case, we can write rho equals to the electric field divided by the current density, or we can write in a vector form, E equals rho J. So you can regard this as the field form of the Ohm's law, because as you know, actually E will be equals to E dot ds. Not V should be equals to this one. When you learn this in chapter 24. So actually, the relationship between the E field and the current density is something similar to the voltage and current. However, in this case, the geometric factor moved to here. This is the geometry. This is another geometry. So rho is not related to the geometry. All the vector goes to the here and also there. And likewise, we also define the conductivity, which is nothing but the inverse of the resistivity. So it is just a definition only. So nothing to mention, I think. So let's have a 15 minutes break.